So we're going to go back and forth, but mostly because I'm going to bore the pants off you with some carbon and climate science, and then Derek is going to tell you all about the economics, you know, the important stuff, the money. No, seriously, I am a huge fan of his. I mean, wait till you see. You're going to love this. And I'm so glad that the University of Arizona has been, they had a ton of foresight in hiring people like Derek so that all us scientists will occasionally take our feet up out of the, put our heads up a little bit and actually see what some of these really big implications are. So I'm going to start like I always do. Remember this? This is Voyager's picture of Earth. I don't know why they call it Earth. They should really call it ocean, because it's 72% water, and this is having a profound impact on our climate, and particularly here in the desert. And I'm going to show you how. So again, blue planet. We really are blue, and we've found thousands of planets circling other suns, other stars in this galaxy and elsewhere, but we've never found one that was blue. So far, we know there must be, but ours so far is the only blue home that anyone has ever found. So as Carl Sagan says, Earth, like it or not, is where we make our stand. Everyone you've ever loved, every book you've ever read, every story you've ever heard, all of these only ever here, this planet, right? And we're making profound changes to it now. So I like to show this one because it looks beautiful, and everybody goes, oh my God, that must be the most gorgeous satellite data I've ever seen. It's not satellite data. That's math and supercomputers. That's a simulation. That is the current weather model for the National Oceanic and Atmospheric Administration, for the National Weather Service. If you looked at your forecast and said, hey, in a few days we might get rain, that's from not a weather model, because 4 weeks ago, the National Weather Service switched from a weather model to a climate model. Everybody says, oh, those horrible climate models, they stink, they must be terrible. I'm like, well, the chief scientist for the National Oceanic and Atmospheric Administration, for NOAA, he likes to end all his talks now with, if you like your 10-day forecast, thank an oceanographer. I'm not joking. I'm going to show you why the oceans have become so critical and why everybody who says, well, it's only warmed a little in the atmosphere, it's bad. It's much worse than you think, because most of the heat didn't stay in the atmosphere. It's in the ocean. It didn't leave, and it's building up, and it's having profound implications. So we've actually had a convergence of weather and climate modeling. You're living it right now. I honestly thought it would take another 10 years for us to get to the point where we could use a climate model. Now, climate models, so weather models are just an atmosphere. Climate models are an atmosphere and the ocean. That's the difference. So they had to switch to one that actually has an ocean. And it happens to be my favorite because it's the one I helped develop when I worked at the Geophysical Fluid Dynamics Laboratory. Sorry. Oh, I'm sorry. Did you say girls can't do math? Come at me, bro. So this is CO2 in the atmosphere, and it's actually two records you're looking at here. One, the one that's wiggling more quickly, that is Mauna Loa. It's at the top of the volcano in Hawaii, and it was started back in 1958 by this guy, Dave Keeling. He actually started the other one that's on there too, which is at the South Pole. They look the same. Outside the variability, it looks the same, and that's because the atmosphere is incredibly well mixed. CO2, as we emit it, goes everywhere within a year. What you emit out of your tailpipe will be detected at the South Pole within a year. Everything is well mixed. So whatever we emit actually has an impact on everybody and everything on planet Earth. We don't just have his records anymore, though. Did you know that that record itself, that one from Mauna Loa, is actually carved on the wall of the National Academy of Science? It's considered sort of one of the great achievements of humans, is that we now know that we are terraforming our own planet in an epic and permanent fashion by taking fossil fuels that were locked into basically a lot of the oil and gas that we actually pump out of the Middle East used to be phytoplankton in an ancient sea called the Tethys 200 million years ago. And then when plate tectonics crunched all this stuff and heated it and warmed it, it turned into oil, and then we put it in our tanks and burn it. Yes, yes. So you're actually getting the harvest of ancient sunlight in your gas tank, and now we're putting it in the atmosphere some 200 million years later in a big rush. So of course it's having a big impact. So we monitor this all over the world now. These are all run by the United States. There are other countries that do monitoring, that contribute to this monitoring network, but what you're looking at is the National Oceanic and Atmospheric Administration and US taxpayer dollars. We know where the CO2 is coming from. This is first order. We know how much there is. All right. So what does it do once it's in the atmosphere? I know this is old hat for all of you, and I apologize. But greenhouse gases are really interesting. The sunlight comes through and it warms the surface, and then it tries to re-radiate back out to space so that we don't just accumulate all this heat. And what greenhouse gases do is they basically scatter or block the outgoing long-wave radiation. So like you would be in a down sleeping bag, the more down, i.e. the more greenhouse gases you put in the atmosphere, the more down in your bag, the warmer you stay. You might have one of those hideous, thin, Walmart-y type bags and freeze your rear end off at the Grand Canyon like I once did, or you'll have one of those lovely big Agnes bags with enough loft and you're nice and toasty. Yes. So we're in the nice and toasty bag now, and we're adding loft to it every year. Somebody will say, well, how do you know it's actually affecting the radiation budget? Well, nice of you to ask. My favorite set of satellites on planet Earth are called ERBE, Earth's Radiation Budget Experiment. And they sit at the outer edge of the atmosphere, and they look out at the sun and in at the Earth. And they measure how much solar radiation is coming in and how much is getting out. Pretty simple, right? What ERBE tells us is the radiation budget imbalance grows every single year. Every year, the same amount comes in and less gets out. So it's here. Where is it? Well, let's talk about that. So we've got climate change indicators everywhere. Temperature over land, sea surface temperature, tropospheric air temperature, ocean heat, temperature of ocean. And these are multiple data sets over the entire Earth's surface. They are extraordinary work done by teams of scientists over generations, literally generations of scientists in these enormous teams. To my eye, it looks like building a cathedral. Man, you got your stonemasons, your glaziers, your architects, people just hauling the rock. It takes a lot of people to do this kind of work, and they've done it. It's pretty extraordinary. Let me just show you a little bit. And this is what you get out of a climate model when you run it into the future. It says that by 2030, we can expect to be much hotter and drier. That's us. We're in the bullseye, right? And for the East Coast, where everybody's going, oh, it's not actually that much hotter, you're like, yeah, really? How much wetter do you feel? Because that's a climate change impact too. Flood after flood. I have friends back in New Jersey at Princeton who have had 300-year floods in the last 10 years. That's how it's going these days. And this is actually predicted by the climate models. It's part of what we think. And I just want to point out that from 1970 to 2018, Arizona was the third fastest warming state. Yeah, you knew that. You feel it, right? It's pretty bad. Well, okay, I could just show you a couple more things. Did you know that Tucson and Phoenix are the number 3 and 4 hottest warming cities? Yes, so we're getting the brunt, which is why it's so wonderful that the University of Arizona and Arizona, the state, have actually invested in studying this and hopefully coming up with some cool solutions. So I have little kids, and this summer we had the hottest September and the hottest October ever, right? Ever on planet Earth and here in Arizona. And to me, that was cabin fever. Oh my God, if I can't put my kids outdoor to play, somebody's gonna be in trouble. No, really, you can only stand so much. They must go outside, except when it's that hot, you worry about them, right? And this is an indication of how many days above 110 for Phoenix. We have 7.9 days since 1970. How many more days above 110 for Yuma? 18 more days. And for Tucson, we go back to 105 because we're not as hot as they are. So over 105, we've got 17.2 more days per year over 105 than we did in 1970. So if you are lifelong Tucsoners, you know it's changed. This is a big difference. We're pushing 3 weeks now. That's not small. And I bet your bills, you know, everybody loves that AC bill in the summer. Boy, it's got me looking at new windows. I don't know about you. We already did the new HVAC. I'm like, what can we do? There must be a solution. Ooh, Derek's going to tell us all about it. So I just want to point out that what we feel in the atmosphere is just this tiny, tiny pink line. This is the total that Irby says is the top of the atmosphere energy imbalance. And it's been growing since way back here in 1970 through, and this is just this plot through 2013. All of this blue is what went in the ocean. It's 92%. So when we say we have an El Nino, that is basically the ocean giving back a tiny fraction of the enormous bulk of the warming that's gone on. Now, there's a big issue with this, which is, how do we know that? So we used to think, okay, we have all these temperature sensors in the atmosphere. We know because we have anemometers on our houses. We measure these things. The Weather Service measures these things. But how do we know what's going on in the ocean? And in the past, we had these huge uncertainties. So if you haven't thought about climate change since the 1990s, I have some news, because we've really changed how we measure these things, particularly in the ocean. So just around Antarctica, everybody's like, why do you study Antarctica? For crying in the beer, why not California be so much nicer and so much closer? Or the Sea of Cortez, and I say, well, why do you rob banks? Because that's where the money is. I'm really serious. Antarctica, the ocean around Antarctica, the Southern Ocean, accounts for 2/3 to all of the ocean heat uptake. It went in there. You're like, why? There's so much more ocean. Because this is where most of the mixing occurs because of the massive westerly winds. They're almost 1/3 stronger than the northern hemisphere westerlies that we experience. Theirs is much more intense, and they have no boundaries, right? There's no big speed bumps like the Rocky Mountains or the Himalayas, so they roar. 2/3 to all the heat uptake goes on in the Southern Ocean. Half of all the oceanic uptake, which means 1 out of every 8 molecules of carbon that comes out of your tailpipe, your tailpipe, 1 out of 8 goes in around Antarctica. 1 out of 4 goes in the ocean, somewhere in the ocean, but 1 out of 8 goes in around Antarctica. So I study around Antarctica because that's where most of the heat and half of the carbon is going. It's a very big numbers, right? And it's because the ocean mixes better there than anywhere. And then, of course, it also fertilizes 3/4 of the global ocean production. So if you like your fish, I have bad news, which is that right now we're actually we're doing what we call nutrient trapping. I won't get into it, but it's bad because not enough of the nutrients are going to be spread out over the ocean to drive productivity. So other bad things happening in the ocean you might not have heard. The 2016-17 El Nino killed half the Great Barrier Reef, and only about 15% has recovered. It's massive. It took 1 million years to build. The last growth spurt's been in the last 20,000 years, and we lost enormous pieces of it. Hundreds and hundreds of miles of reef died because it was too hot and caused them to expel their little algae that grows in their skin. And once they expelled them, the heat didn't come back down, so they all died. It's terrible, actually. So I've been giving talks about these sorts of things for 15 years. And 15 years ago, I said, oh, you should definitely go see the reef. You want to see it while it's still awesome. I can't promise you that anymore at all. Now, that heat that's going into the ocean, that mass amount, is also raising sea level. So Norfolk is our biggest naval base, right? And this is what's predicted with 1.5 degrees warming. The blue is underwater. At 2 degrees warming, you're looking at it. And here's after 4 degrees warming. It's entirely underwater. If you knew that the enemy was coming to get your biggest naval base within 15 or 30 years, what would you do to prepare? What would you do? What would you sacrifice? What would you pay to make sure that that didn't happen? And yet, right now, we're in the process. I'll just say, going to sea is very hard. So how do we know what the ocean's doing if that's the bulk of the warming? How do we know? Well, we didn't used to know as well because we had to go to sea. I spent my graduate work, I've been out to sea and around Antarctica for about a year of my life on different cruises all combined. And it's very bad weather. It's incredibly rough. The waves can be 100 feet high. That's not a joke. Meaning you're on the 3rd deck at the bridge, basically, on a 300-foot ship, and it towers. A little spritz on a good day, just a little water droplet. On a bad day, it's blue because you're getting buckets on the bridge. And when it's black, when you dig the prow in so far and an enormous wave just rolls over the ship, it makes you feel like a little tin can. That's how hard it is to go to sea, which is why we didn't have enough measurements before. All right, so climate models have an ocean. They don't just have an atmosphere, they have an ocean. They solve these equations, but they also solve them for the ocean. Now, we could do just the physics, but I also add the biogeochemistry. Why? Because the carbon. I want to know what the response is of the carbon, because it has this wonderful feedback. Okay, it's a terrible feedback. So climate modeling has been growing in complexity and skill. So basically, these are climate models that we did not use for weather, did not use for weather, did not use for weather, is so good we're using it for weather. Yes. Seriously, we're using it, the Weather Service has adopted it now. And we're using more and more computing power. This is Moore's Law. This is in petaflops, teraflops, gigaflops. You can't believe. I started working at the Geophysical Fluid Dynamics Laboratory right about here, and it was still an incredible increase. It makes it expensive and hard to do, but it's really working now. So this was the first climate projection by Wally Broecker, who used to visit us here at UA every year and sleep on my couch. No, it's not a joke either. And these are the actual records of what has happened to temperature in the atmosphere since 1970 through 2013. And this was his prediction. This was the prediction at Jim Hansen's prediction, and you can see it's even better, right? This was in 1981. This was the IPCC first round, dead on, and they made this prediction back here. This is the one from 2007, and they made this prediction back here. This is the one from 2013, and they made the prediction here. You can see we've been telling you what's going to happen, and then it comes true for 30 years. On the nose, we've got this. We've totally got this. So everybody says, well, I don't trust those climate models. I'm like, okay, we're using them for the weather. We nailed our predictions. What more do you want? Well, okay, we've got more. So Jim Hansen gave his big testimony, global warming's begun, in 1988. President H.W. Bush was the one who got us into the UN framework on climate change, which actually is this has been ratified, this is what we've agreed to, and this was stabilizing greenhouse gas concentration in the atmosphere that would prevent dangerous anthropogenic human-induced interference with the climate system. This is actually what he read. This is part of what we agreed to. And then in 2013, this new report came out that said back in 1990, they didn't even quantify the role of humans. The balance in 95 was the balance of evidence suggests a discernible human influence. In 2001, we said likely, 67 to 90% chance. In 2007, we said 90% chance. And in 2013, we said extremely likely, at least 95% chance. So we've been getting better and better at this and more certain. And if you haven't looked at this since the 1990s, you should take another look, because things have come a long way in both the science and actually what we've done to our atmosphere. So I'd like to show you just a little bit about what we're doing here at the University of Arizona. We've been very fortunate and had great support from the university here, and fantastic students, I might add. My grad student Stan just got back from deploying moorings at sea, and now I'm going to actually show you some of his figures. They're coming. And my student Becky is graduating with her PhD in February, and before she goes, she's spending 2 weeks at the Hadley Center, the Met Office for the United Kingdom, for England. They've invited her to come for 2 weeks, our graduate student, to help them fix their model. I know, I'm so proud of her, I can't tell you. So some models are better than others. I'll actually point out, there's the UK model, and this is the GFDL model. So they're good, they're very good. But they would like to be as good as we are, yes. So we've been building better evaluation of these models using Sciverse, which is an incredible resource here at the University of Arizona. Every single one of you can come on in and see the calculations I've made, the data that's available, the models that we run, the data visualization software. I have digital toolkits. I have digital tool sheds full of toolkits. You're welcome to all of it. I know you don't want them, but they're available if you'd like, because we're into radical transparency. Steal this book, please. All my colleagues, all we're trying to do is accelerate discovery in this way to help save lives and property. So what is the incentive to let anybody, I'm not going to hang on to one little bit. In fact, I'm going to push it on all my colleagues like an evangelist. It's terrible. I am awful. You definitely don't want to sit next to me on a plane. So we threw a little a workshop to build better evaluation tools here at the University of Arizona called the Great Antarctic Climate Hack. And we thought maybe 10 or 15 students might come. And we had over 150 senior scientists from around the world logging in online to participate in our hack. It was, by the time we were done, our t-shirts looked like NASCAR because the University of Arizona is doing something quite extraordinary, not just in the sense of open source, not just in the sense of better measurements, not just in the sense of better modeling, but in community building. We are a collective powerhouse, and it's just wonderful that I get to work with Derek. So just 2 seconds, Derek. So we've built these collective tools so that now we are so good, we need to improve the observations. The models are doing terrific. What we need is to know the observations need to be better. So robot floats, I know. If you've seen me talk before, I'm a little obsessed because they're awesome. Because we leave them behind, we go out on a ship, we leave them behind, and they will make 250 profiles over the next 5 to 7 years of data, and they will beam it back by Iridium satellite. And I'll be able to put it on the web in real time. So you can actually see the ocean, both the temperature warming, the acidification. You can go click on it right now and see who's popped their head up today. You want to see what's going on? And it's all available on the web. We don't hold any of it back. And we ingest this. The Weather Service is already using all this data to help improve our forecast, which is, again, if you like your forecast, thank an oceanographer, because this is part of the innovation. This is part of how we push the world forward. Not just us, because I have to say, there is a profound component of American leadership in science that I think sometimes is underestimated. We're like, well, why can't they do it? Because they don't. I don't know why, but we do. And when we do, we make the world change. It's quite, let me show you some. So this is what all the ships together in academia, not just the US, but all of them together, including everything we could get from the Navy. That's not that much. So you're looking at an oceanographer's plot where, of course, the continents are gray and blank. So if you don't recognize them, this is Asia, this is North America, this is South America, and the lit up parts of the ocean. And this is what it looks like with robot floats. Sorry. We actually have many times, 3 times more measurements made by robot floats. And we didn't even have any in the water till 2004. My robot floats with extra pH sensors and others to measure the carbon in the ocean didn't come out until 2012. So you're living through a revolution in oceanography. Up until then, all we ever could measure was from a ship. And since the Cold War ended in 1989, we'd had fewer and fewer ships because as we mothballed the fleet, we did not replace them. And so we had fewer and fewer measurements. Now we're back to growing again, and we're growing because we are sneaky and awesome and have built things that can help us do our work. So I actually was going to show you my student actually deploying. These are the way we used to do it. We actually deployed these great big huge rosettes. Now this is a pretty calm day and it's pretty easy, but it's much worse when it's bad outside, I'll just tell you. So we lowered that down to each one of those bottles. We literally would pressure sensor trigger it at different depths, fill it with water, bring the water back to the surface, and then make a ton of measurements off the water we pulled up. That's not really in situ, it's in a bottle, right? We bring it up and look at the bottle. What we're doing now is we put microsensors on a float that actually goes down and makes the measurement right where the water is. And we do it over and over. This is all the complicated measurements. You're standing in hip with freezing feet and freezing hands, and it's very hard work. And a lot of these cruises, when they're very far away from land, have long transits, so they can be as long. My longest cruise is 56 days, and you're working around the clock. It's exhausting, and you can't make a mistake because somebody will get hurt. And this is my student Becky muscling one of our floats into the water. So you can make about 5 profiles on a ship in 2 days. That float will make and it costs $100,000. That float costs less than $100,000, about 75 grand, and it will make 250 profiles. So 5 for 100 grand or 250 for 75 grand. It's a profound difference. We make way, way more measurements for way less money, and we can see it in real time. We don't have to wait till you get back and docked and then put the data online and all the rest of it. It's just like that. So it's pretty cool. They sit at 1,000 meters, they drop to 2,000 meters, and they come to the surface. Why am I telling you this? Because that's where the heat is, that's where the carbon is, and this is the innovation that is driving our understanding of exactly how many carbon molecules there are and where they are on planet Earth. We are getting so much better at this, and the water and the heat. So, blah, blah, blah. So we have this great program. It's joint with a bunch of my friends, Jorge Sarmiento at Princeton, and a friend of mine at Scripps, Lynn Talley. So this is Hannah Zanowski, a UA Wildcat, yes, who was in my big oceanography class. You guys are not even close to the biggest audience I've had today. I have 750 students in my oceanography class. Did you know the University of Arizona teaches more oceanography than any other university in the world? We do. We do. We teach almost 2,000 students a year. And when they graduate, almost 20% of Arizona students have taken oceanography. They know how their world works. They do. I mean it. It's pretty extraordinary. And that actually from the desert. I know. Isn't that great? So Hannah graduated from here with a double major in math and physics. She went to do her PhD with my friend Jorge at Princeton. And then she is now employed as an oceanographer at the University of Washington. I know, from the desert, ha, ha, ha. The students here are extraordinary. These are our floats out deployed. Those are all the data points. This is a map that my grad student Stan made. And what you'll see is these are the floats as they start making measurements, each one as they're deployed. And this is like over time. So what you're seeing is their actual data, pop, 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 pop. Each one is about 10 days in between. Float after float after float. Some of them are moving very fast. Some of them are moving more slowly. It depends on what current they're in. But they make a measure. They make these long profiles every 10 days. And this is what we started with. 0. So when they make these measurements, we basically end up with these long. Look at this. You're actually watching the ocean acidify in real time. Acidification, the pH drop in the ocean, you can see it within 13 months, the difference between normal, like natural, and not natural, human-made CO2. Only takes 13 months. You go January, February, March, April, May, come back around January, oh my God, it's much lower. And then the next year, it will be lower yet. That's how fast we're accelerating. And we can actually calculate the carbon flux from the ocean to the atmosphere, which we are now using to actually figure out where every molecule of carbon on Earth is going. We're still in the process of building this system, but I'm really excited about it. We assimilate them into these great models. And so what we're going to do is we're going to take all of the sources of carbon to the atmosphere from humans. We know where they go in the atmosphere. There's very low uncertainty. We are going to lower this uncertainty, and then we're going to be able to calculate what everybody's doing on land for the top 10 economies. We're working on that right now. So we think that reducing uncertainties in the ocean sink can reduce the total uncertainty and the global constraint on the carbon budget. This carbon budget is going to let us say, China, for crying in the beer, you lied to us. You told us that it was only this much, but it's 23% higher. Come on, we got to do better than this. And I don't think you can do it without maybe actually naming it, you know, who did what to whom. And the reason I'm excited about this is because the United States is emitting 15% less carbon today than they were in 2007. Did you know Arizona our peak carbon was in 2007? Arizona carbon emissions are dropping annually. Part of it is that we're actually burning less coal, but I'll show you later. But Derek's going to talk about what the implications are. I'm really excited about this, Derek. So this is where I'll start next time.
I want to thank both Joellen and the Brown Foundation for putting this together. It's really, I think that the fit's going to be pretty interesting between the 4 different pieces of the talk. So the idea is I'm going to now talk about the actual economic challenge of climate change. Why is it an economic problem? Then we'll turn back to Joellen and talk about how we can actually monitor emissions using the ocean. The ocean's the key to everything, as we've seen. And then at the end, then we'll come back and we'll look at how we can actually use economics to help solve the climate problem. So we'll kind of keep iterating back and forth like that. So we just passed Halloween. There was free candy out everywhere. I know there's free candy out in our department. Tend to eat a little bit more of it when it's sitting out in a bowl rather than when it's locked behind a vending machine. So when a bowl of candy is free, you tend to eat too much of it. And the basic economics of climate change is that when emitting carbon dioxide is free, we tend to emit too much of it. And we can more or less go home. That's most of the story. So there's a sense that climate change is somewhat locked in. And it's actually not true. The next 20 years, probably not a lot we can do to affect the trend. But beyond that, there actually are still a lot of open choices. This is history, 1950 to about 2010, and this is a high emission pathway, basically the pathway we're on and have been on, going out to 2100. The warming out to here would be an ice age in reverse, about 4 degrees of warming, but over the scale of a century instead of 15,000 years. So that this would be a pretty rapid change, pretty different planet we'd be living on. You'd think about an ice age, New York's under a mile of ice, take that and do it the opposite, it would be pretty different. This is if we follow a low emission scenario, and there the planet would look different, but not radically different from what we're used to. We'd be under 2 degrees of warming. And obviously we can do anything in between. So where does economics come in? Well, one, where should we be aiming in there? Should we be aiming more toward here, somewhere in between, something up here, something down here? What should we be doing? The second is, if once we decide where we're going to aim, how do we get there? How do we actually reduce emissions? It turns out we're going to have a lot more to say concretely about number 2 than number 1, but I'll tell you what we know and don't know about number 1, and then come back after Joellen and return back to number 2. So we all know about the bureaucrats that sit in the Office of Micromanagement over in Washington, D.C., and they're regulating the price of gasoline, telling you how much diesel can be sold for in California versus New Mexico and Tucson versus Phoenix, and the same thing with regular versus premium gasoline. They do the same thing for pencils, kind of monitoring pencil inputs and outputs and supply and demand and trying to match these things up around the country. iPhones, if Apple wants to do an iPhone release, they have to run that by the government. They actually have to get it approved. The government then actually tells them what price they can charge for the new phone, depending on how much better it was year to year. Other kind of apples, Red Delicious, Granny Smith. If we think that Red Delicious are actually waxy and cheaper because of the market, but it's actually the government kind of told them they had to do that. It's regulated. So actually, this isn't the way most of the US economy works. There are some sectors that work like that and have worked like that, but we don't have that office. This is a very different kind of economy. For the most part, we use markets to make these kind of decisions, and understanding why we do that is critical to understanding how we can actually help address climate change through markets. So markets can be thought of as like a giant algorithm. Data is all the rage these days, so think about an algorithm like Google. And what markets are taking in is all this data about how much does it cost different factories where to make different things. How much do each of us care about different things that we might be buying? And they're taking all this data in every day and trying to allocate resources to decide how much of what are we going to make and who's going to be the ones to make it and who's going to be the ones to buy it. If we had all that data available to the government could run a computer model. Several of us in this building could probably code that model and help them out with it, but nobody has the information. I'm not going to tell the government, and hopefully I'm not going to tell Google, and no one firm's actually going to know all that stuff. So emitting carbon dioxide does impose real costs. There are real costs to society, as we'll talk about, but those costs are not part of the market. The atmosphere is a free dump, basically, for carbon dioxide. So if it's free, then firms, unless they're altruistic, don't necessarily have a huge incentive to really incorporate those costs. They're going to end up emitting too much of it, exactly like eating the candy out of the jar. So environmental economists are obsessed with market failure. Markets work well in lots of cases. Interesting economics tends to happen when they don't work well. So we spend a lot of time in the econ department thinking about markets that don't work as well, whether it's healthcare, environmental, energy, other examples we can come up with. So that tailpipe in your car, if that were pointed the other way, I promise you wouldn't drive nearly as much. You would cut down your mileage very quickly. But instead, you spit that out so that the person biking behind you or running behind you can breathe it. The Grand Canyon, there are markets associated with the Grand Canyon, but the value of the Grand Canyon is nowhere near reflected in these markets. I think there's Joellen sleeping on her sleeping bag, freezing, and the value of that isn't really reflected. I was on a plane with some middle school students from Lafayette a few days ago, and they had just finished going to the Grand Canyon for a week, and they were saying, oh, and last year we got to go to Arkansas. I was like, oh, Arkansas is pretty. I spent a lot of time there as a kid. That's one of my favorite states. I was like, how did you like that compared to the Grand Canyon? They looked at me like I just escaped out of an insane asylum. They're like, the Grand Canyon was cooler. I was like, okay, that's fine. Polar bears, endangered species, that a lot of value, not captured in markets. I may never see one. I may be happy staying in a warmer climate, but I may still care one way or the other. And things like copper tailings ponds, I think this is from near Bisbee, I think. In that case, that could be part of the market. You can sue if there's an insult to you from that, but the firm may not be there anymore to pay, in which case, how effective is that going to be? So climate change might be the mother of all externalities. It's a common phrase to call it that. And the basic idea is an externality, or at least the ones we care about, are non-price effects of a transaction on people who are not party to the transaction. So two people agree to do something that affects a third party. And that really breaks the logic of the price system. So what we like about transactions is that any voluntary exchange is creating value for both parties. Both parties agreed to it. If it didn't create value for them, then one party should have not agreed to it. And if two people can find each other and make a mutually beneficial trade, that's a good thing. We're kind of improving overall well-being. If a third party is affected, then maybe it was still a good thing on net, but maybe it wasn't. And in a lot of cases, it might not be, and that really breaks the logic of the price system. So prices aren't going to be conveying the right information. In computer science, you build a model, you say garbage in, garbage out, no matter how bad the model is. If the market's collecting the wrong data about cost and then using prices to allocate resources, it's going to allocate them in an incorrect fashion, maybe almost correct, maybe pretty far from correct. It's hard to say. So the current price of emitting is close to zero, but emissions aren't really free. So then what should that price actually be? How do we think about it? So what is the correct price? So in order to figure that out, you have to think about adding one more unit of carbon dioxide to the atmosphere. It's a thought experiment. Then how does the CO2 in the atmosphere and the oceans change over time? How does the heat in the atmosphere and, of course, the oceans change over time out into the future? Then how does that affect things that humans care about? That's a really hard chain of things to solve, and in a sense, actually, I mean, no slight, but like the actual mathematical part of that, of the carbon and the heat cycle, are actually the easier parts of that, because what does that then affect things humans care about is really uncertain and hard to figure out. So things like agriculture are going to be really effective. There are going to be benefits. CO2 fertilization in some areas like Canada are going to be able to grow more crops because it'll be warmer. We'll have longer growing seasons are good. But there's also going to be more extreme heat in a growing season, and some areas are already plenty hot, and there's going to be a lot of damage from that. There's some conflicting effects, and it's hard to know how everything will change. Fish stocks. Warmer water holds less oxygen. More acidic water has consequences up and down the food chain. Going to be problems from that. I think you're already documenting decline in fisheries as we speak. Drought. They typically say wet places get wetter, dry places get drier. I don't think I need to say too much more about that here. Big storms. So warm water is the fuel for hurricanes. Harvey dumped 50 to 60 inches of rain on Houston. So 5-ish years, 4 to 5 years of Tucson's rainfall in the course of a day to 3. That's a lot. It's a lot of rain. Probably could not have happened without warmer water fueling it. It would have been extremely unlikely. A lot of disease vectors are temperature limited. You warm, they can move further. What are the public health impacts of that? How much of that can we just offset by doing basic public health stuff? How much of that do we have to live with? Coral reefs, really vulnerable both to warmer water and acidification. Joellen already touched on that. Obviously a big value a lot of people care about and important for fisheries in its own right. Sea level. There's a country about the size of the United States that is within the realm of plausible sea level rise over the century, and a chunk of it's probably not even just plausible, but more likely than not to go underwater. Implications of that are pretty enormous. Energy use, Joellen also touched on this. Warmer weather, we're going to use less heat, that's a plus. You're going to use more AC, that's a cost. How does that net out, and how is that different around the world? And then one more, and one of the bigger impacts, there's a lot of just purely non-market impacts of climate change. The ecosystems that we're used to are just not going to be the ecosystems that'll be there in 100 years if we follow even a moderate emissions scenario. What are the costs of just trading out a world we're familiar with for bits and pieces of a different world we've chosen to protect? Really hard valuation problem. We're not good with valuing big unknown changes like that, and that's probably a big chunk of the story with climate change. So how could you do it with data? Economists, despite reputation, prefer not to make numbers up, but prefer to actually use data to get numbers somehow or other. So what could you do? So you might notice that there are climate zones around the US. You may have heard that Tucson's climate is pretty different from the climate in northern Illinois right now. And in general, I think it's usually going to be true. So, okay, well, why don't we just compare stuff going on in Illinois, farms in Illinois, to farms near Tucson, and see if being in a hotter climate is good? Maybe factories make more or less in hotter places, or maybe farms make more or less. The problem is there are lots of things that are different between Tucson and Chicago that are not just about the weather, and they often, institutions and property rights and systems of government and who settled there and just all kinds of things are different. The quality of the soil, things you can't measure. And so doing that analysis doesn't really work because you're capturing all kinds of stuff that might not be climate. Okay, well, what could you do? Well, you may have noticed some years are hotter and some years are cooler. We saw this in Joellen's slides with the temperature bouncing up and down year to year. And even the climate models don't forecast exactly all those wiggles. Some of that's just random variation. You kind of learn it after the fact why it happened. So that's kind of like an experiment. We can randomly get a hot year some year and randomly get a cold year some years. And did we grow more food or did we make more stuff in hot years versus cold years? There's a lot of economists that do this, but the problem is that weather isn't really climate because people might do different things in response to climate than they would to weather. If you knew the weather was always going to be hot, you do different things than if you think it's a one-off hot day or hot year or hot month. So some of my own recent work, I've been actually trying to show how you can estimate climate effects from weather. And then when I do what comes out of that and apply it to agriculture, I find $20 billion annual losses by the end of the century in the eastern US alone, which is a much bigger number than I anticipated. And this is the first theoretically grounded estimate of that number. And it's in line with some back-of-the-envelope calculations other people had done. So our knowledge of the cost of climate change is staggeringly incomplete. We have very little idea as economists. The Nobel a year ago was given for economists trying to figure out what the costs of climate change are and what policies should be. But even with that, we still know so little that it's hard to say that we can give a precise number, unfortunately, because governments would like a number coming from us. So there's a lot we know we don't know. There's much that we don't know we don't know. There are a lot of things that we may never know. Even after having lived through climate change, it would still be a hard problem to look backwards and figure out what all the costs were. Nevertheless, to do it before we've run the experiment. And that just might be the situation that we're in. So if economists say policy should be X strong, take it with a hill of salt because we don't know a lot of the key inputs. And I'll come after Joellen to exactly what we do know. And one final thing, so the models that underpin policy recommendations and what the Nobel is given for all also abstract from uncertainty, in addition to not knowing actually what climate change is going to do to stuff. So by abstracting from uncertainty, within the model, they assume that everything's going to go a certain way, and you know the way it's going to go. Uncertainty is probably a pretty big piece of climate change, whether it's uncertainty about warming or uncertainty about what warming means for the economy, or even uncertainty about background economic growth. All these things are important. And in some of my work, I've been showing that if you ignore uncertainty, you could get a recommended carbon price of like $13 a ton of CO2 using kind of standard calibrations. If you throw uncertainty in about economic growth and warming and damages, and it's a hard problem, that's why people don't do it, but if you figure out how to do it, then it turns out you want to save more because you're uncertain about the future. You save by reducing emissions because we're giving ourselves future wealth by reducing emissions today. You're also buying insurance against future bad climate outcomes by reducing emissions today. And both those channels lead you to actually double that recommended carbon price, and you're missing that big doubling if you just use a model where you assume that you know everything about the world. But one thing we do know, the correct carbon price is not zero, so then when I come back, we'll talk about how we implement the price, and in the meantime, we'll talk about how we can actually enforce matters internationally as well.
All right, so I want to go after exactly who's emitting how much. There are several ways to do this, but I'm going to start with trust but verify. We have carbon agreements now. We are pulling out of the current Paris Agreement, but trust but verify. I think we'd all be more willing to be in an agreement if we knew that we would all be paying for our emissions and not for everybody else's, right? So the Paris Agreement is exciting because everybody volunteered, each country volunteered that they would cut some of their impact on the atmosphere. And that doesn't just mean carbon. It could mean methane. It could mean changing deforestation. When I'm not going to talk about equity or in this particular talk, but if you were, the worry is it used to be that they thought developed countries are doing all the fossil fuel emissions, so we really owe it to the developing countries to help them with this. Now that might still be true, but we've now done better carbon accounting, and it turns out deforestation has had very nearly 2/3 to equal amounts of impact. I know that sounds like it can't be, but you wouldn't believe the impact from land use change, basically cutting down big chunks of the Amazon, the Indonesian rainforest, et cetera. And we actually have what we call afforestation in the United States. We're actually reforesting huge areas of the Northeast, the Southeast, and even the West, where we've got mass shrubbification going on due to CO2 fertilization. So it's not as straightforward as you think. Now, this is the fossil CO2 emissions and 2018 projections. So this is everybody. Oh, that is a big number. This is China, and they claim that it's flattened out. Anybody believe that? I have a very nice watch, I can tell you. There's even a bridge. No, seriously, they voluntarily, in 2010, they voluntarily revised their emissions estimates by 23%. Said, oops, we burned more coal by 23% than we thought. 23%. And we missed it. I didn't know that they'd been lying. Oh, excuse me, made a mistake. I didn't know. This makes me extremely cranky because I'm a scientist. This is what I measure. I should have been able to see it, right? Well, I didn't have my robot floats out then, right? So I couldn't measure the ocean component. So they blamed it. They stuffed it under the ocean rug. They basically said, we didn't emit it. It was the ocean. The ocean. Now, the good news for us is we are 14% down on our emissions since 2007 and dropping every single year. The United States is doing great. We did get a little increase in 2018, but we're doing better this year. It's actually quite extraordinary. Did you know, without any government help, that Americans have basically volunteered to reduce their emissions? Now, part of that is fuel switching. It's just plain economics. They didn't like coal. They're doing more natural gas, and it's now cheaper. Solar panels, cheaper. But then again, you're like, well, is it all about just being cheaper? Because I see an awful lot of people with solar on their roofs, and I know they haven't made their money back yet, right? You know they haven't made their money back yet. So they're actually investing in their values. They think that it's better, healthier, and they'd like to save a buck, so they're doing it, even though it costs them money now that they may or may not recoup, depending on how much it costs. So it's an amazing thing that we're dropping our emissions without actually anybody getting organized. No, really, nobody said you had to. Okay, that's not true. Let's go. It turns out that the Massachusetts versus EPA was in 2007. They sued with 14 other states, the EPA, for not regulating carbon dioxide as a pollutant under the Clean Air Act, because it says on the Clean Air Act that pollutants must be regulated. They said, I'm being caused harm. Massachusetts said, my sea level rise is eating my shores. I'm actually smaller as a landmass because of sea level rise. I want you to regulate it. And the Supreme Court actually ruled, yes, it does have to be regulated. So I always look at that 2007 was our peak emissions, and all of a sudden it's coming down, down, down. I'm like, So even without an actual regulation, meaning the rule, how we're going to regulate it, we're doing it anyway, both industry and regular folk. So, and by the way, they only cited one brief in their ruling, and it was the scientist brief, and I'm one of the 13 scientists. And did you know it's organized by the University of Arizona? Yes, it was us. No, really. So, and Kirsten Engel from the law school, Scott Zaleska, who used to work for the Massachusetts Attorney General, and Scott Zaleska from EEB, from Ecology and Evolutionary Biology, myself, and others. Yeah, okay, so that's the rule. We have to regulate it. So bottom up is what I just showed you, where self-reported, which is why I don't trust all the numbers, because it's just what they said they emitted. I don't know. How do I tell? I'd like a top-down constraint, a science-based certainty about who emitted what, who is dumping. Because how can you, I mean, I know we can put costs on it internally to the United States, but I'd like to be able to, I don't know, somebody said, don't call it name and shame. I'm like, yep, that's what I want to do. That's the one, that's it exactly. So this is the US energy consumption in 2018. And you'll notice that here's the electricity generation, and this is how much we're basically rejecting. We generate all of this and we only use this. That is cranky making. How about let's think about that. Balancing a load might really help. Ooh. So here's solar, nuclear, hydro, wind, geothermal, natural gas, coal, biomass, and petroleum. These are the ones, this one, this one, this one, this one. These are the ones that actually contribute to the atmosphere, right? And again, you can actually look at the rejected energy from transportation here and from industry. This is massive. Basically, we use 32.7 and we reject 68.5. That's basically 2/3 that we're not really taking advantage of. I don't know. I feel like we ought to not have any new generation and just kind of, use what we got. I would think. I want a battery for my house. If I had, and they gave me cheaper energy at night, I would basically just charge up my battery at night and never, ever, ever make my load big again in the afternoon when they charge you extra. So I'd be saving money and the planet. Yay. And I don't even have to put a solar panel on my roof. I'd just be using our power more efficiently, right? So it would be cool. So I want to show you what that is in carbon emissions. This is all from Lawrence Livermore National Laboratory. Here, 0.0000. Wasn't that cool? And then there's natural gas, coal, biomass, and Biomass is 0 too, because it's a net. We grow it and then we burn it, and we grow it and we burn it. And then there's petroleum. That's it. We can do this. This, by the way, is 2007 emissions. So total is 5.991 gigatons of carbon. This is 2014. It's even lower today. Yes, 5.4 gigatons. We can do this. Everybody's like, oh, it's such a big problem, wah, wah, wah. I'm like, no, we're crushing this. We can totally do this. And just by the way, don't forget what we're not using. We're just generating and burning it, blowing the turbines with nothing. I hate that. We could do better. We could do better, especially with distributed batteries. Everybody says, well, we can't make a big battery plant. I'm like, no, you can't. But if we're willing to put solar panels on, why not batteries? I mean, a Tesla battery would do me fine if it was just a little cheaper. So Arizona actually has a really interesting mix. Our end-use consumption by source, excluding losses, is coal, 5.3, which is 0.6%, 10.8 for natural gas, 58% from petroleum. That's for our renewable energies, 2.9. And so for our total electricity, this is 20.7.7. So, and this is our consumption, 32 coal, et cetera. We have the biggest nuclear power plant in the country. Palo Verde provides about 40% of our electricity all by itself, and it's paid for, right? The plant is paid for. It was big investments by our grandparents who thought big and built big, and our hydropower too. So we actually have an incredibly green mix when you think about it, because we're solar. We're like #2 in the country in solar for states. We've got the biggest nuclear power plant in the country. We've got huge hydropower as well. And we're reducing our coal almost annually. Every year we're reducing how much coal we use. So in fact, there is a serious possibility with a little oomph that we could be one of the first green electricity states in the country. Now, we'd still have to work on cars and transportation, but imagine that our energy mix for electricity went to 0 carbon because we already have backbone big investments that are already paid for, already here, already extant. Why not? All right, so what I'm going to do, the science I want to do, is I'm actually going to get us closer to attributing those emissions. So we know the atmosphere really well. We're getting to okay, so I have a couple of updates. So my SOCOM project got funded in 2012. And we just got re-upped again. So we're funded through 2025 to put out another 200 floats. And then we just got a reverse site visit at the National Science Foundation for what they call mid-scale research infrastructure for 500 more floats to do the world. We were going to wait, and we were hoping that our partners internationally would actually match us, because we already have almost 200 floats in the water. We were hoping they would cough up. We'd just be half, but they didn't, so we don't care. We're going to get the globe anyway. So really hoping National Science Foundation, woo, they could fund our 500 additional floats. And that would do the world, we think. And we did the experiment where we sampled one of my fantastic models and figured out that it would take somewhere between 500 and 800 floats. Remember, we get 500 more. We already have 200. I got 200 more I'm putting in. We're going to have enough to do the world. Really, seriously. By the next time I come talk to you, I'll have it. So this is what we calculated. I just want to point out, this is what we have today. Now, it's not all our floats. There's some right here that are European, there's some right here that are Canadian, and there's some right here that are Australian. But the rest of them are ours. I know, it's kind of awesome. And this is us planning it. That's me in the pink scarf. In Villefranche, we tried to get the other countries to bite, but apparently everybody else is broke and they're whining about it. So we just figured we'd go to the National Science Foundation and tell them that this was the coolest project ever and see if they bought. And it looks like they did. So we're also in the UN Global Climate Observing System now as our own call out for these biogeochemical floats. So if we know every carbon atom in the atmosphere, and I can track every carbon atom in the ocean, what's left? What we did. It's the land source or sink, which is pretty much a source from almost every continent. Now, I can't do things as small as Ecuador. It's too small. But I can do the top 10 because we're talking about massive land masses. Russia, China, India, the US, Canada, Europe, Brazil, Australia, Indonesia. I got this. I totally do. So we're assimilating all this data into a big model to build the next generation carbon verification system. Yes, right here at the University of Arizona. We're going to change the world. I mean it. We're doing it right now. So we put in a satellite proposal last year to NASA because I want the winds over the ocean in really high def, high detail. We have some right now, but the American scatterometer pooped out a few years ago and we haven't replaced it. And the scatterometer is how we do this. So I've come up with a friend, an engineer from BYU, who has a small sat concept for a new satellite that would do it. So they spend about $1 billion to put each one of these up. We're going to get it for less than $100 million. So we're putting in a new proposal. Now, last time around, he was the PI, and I was the deputy PI and science team lead. And as of yesterday, I'm the PI, woohoo. So, and just one other little note, I can't believe this, you won't believe it either. Did you know that the Earth Sciences Division at NASA has never in their entire history had a female principal investigator? Not one mission? Wouldn't it be nice? And did you know we're Hispanic serving too? Yeah, this is gonna be great. So we have a plan to put up the satellite. So we're gonna do robot floats, supercomputers and climate models and satellites right here in the desert. And hopefully, 10 years ago, we didn't have an international political agreement to address the carbon cycle. We didn't have carbon-serving satellites. We didn't have Earth system models that could handle the carbon. And we didn't have biogeochemical Argo floats, these robot floats. We have all the pieces we need now to do this. It's actually, I have a prototype of this assimilation system, but the numbers are still ugly, so I can't show them because I don't have enough of my floats out, but I will. They're coming every day. So what we'd like to do is eventually put up some tall towers and actually do it regionally for Arizona. It's my favorite project now is OASIS, Opportunities for Arizona Innovation and Sustainability. I'd like to actually demonstrate our emissions from the state of Arizona. And I know that sounds crazy, but I think we can do it. We already have a weather model that can handle the carbon. We're already running it here at the university. And we'd like to put up more tall towers like they have at NAU, basically do a very sparse picket fence on the northern and eastern borders because most of the air blows in from this direction and out that way, and actually look at the impact of Arizona on the emissions of the atmosphere. And if we could figure out good ways, not greenwash ways, but actually effective ways to reduce our emissions, we'd also be improving our air quality, which has the knock-on added side benefit of reducing mortality among asthma victims, as well as increasing survival of small premature babies, et cetera, because they have the biggest trouble with suppressed immune systems and air pollution, and there are lovely studies that show this. So we'd actually be saving kids and saving money and saving our atmosphere and demonstrating how one saves the planet all at once. And I'd love to do it from right here. We're working on this. Don't worry, we're gonna get money from the feds. So we're gonna actually bring money into Arizona to help do this, so not to worry. So what comes next? We're gonna build out our array of BGC Argo floats. We're gonna get Zephyr, my new satellite project, up to calculate our carbon weather. We're hopefully gonna send the top 10 economies their monthly carbon bill. It won't be a bill, but maybe, I don't know. How much money would it cost? No, wait. It's not a bill, it's just an accounting of what your impact was. And so, if any of you have a Nest, and it sends you a report once a month that says, you did a more efficient schedule, you get 3 green leaves. I'm like, yay, green leaves. And then there was the summer I was pregnant and I was hot all the time and I cranked the AC down so hard, I got black leaves every month. It was terrible. They're like, you're terrible, stop that. I'm like, I'm hot, I'm dying. So we can do this, it's possible. We already got our hands on all the tools. It's actually just technology, elbow grease, and a lot of hope, like a lot of community-based big hearts. Because in fact, we're already doing it, solar panels and everything else. I just want to account for how well we're doing it, and I think the science will bear it out. So that's my last slide. Thank you.
Okay, so we've heard a little bit about the scientific background, about the economic problem posed by climate change, about how we can begin monitoring countries' emissions in a more real-time type way and possibly more realistic type way than we currently do. So how can we actually implement policies to reduce emissions? What can we do? Okay, so we're going to step back a little bit and imagine that you're a pencil manufacturer. So the idea is that your birthday, between 1 and 31, your day of the month that you're born on, I would bet a good bit of money everybody's going to fit within that range. So you made $2.50, and if you were on the 17th, you would have probably chosen not to, right? So probably the right people chose to make a pencil because they were actually creating value for society, and the ones who weren't going to create value didn't choose to. And we got to about the right outcome, provided the market correctly decided or told us what the actual value of a pencil might be. So nobody had to tell you what to do. Just by seeing the price, use your own private information about your birthday to decide whether you're somebody who should be manufacturing or whether you shouldn't be. So the right people are going to make the right amount. We'll get the right number of pencils made in total, and not just being made in total, but being made by the cheapest people, by the ones who can make them at least cost. And that's a really nice outcome. That's why we love the market to get that kind of outcome. Now you're going to make pollution instead of pencils. So something a bit more interesting possibly than pencils. So again, we're going to use your birthday. It's probably still between 1 and 31. Probably actually hasn't changed, so you don't need to look it up again. And that's now going to determine how much it costs you to get rid of your pollution. So you're just sitting there wafting stuff in the air around you, and you're contaminating the air, and it costs you some amount of money to clean up. You could get clean if you chose to. So you're causing $15.50 worth of harm to the whole room by doing whatever you're doing, just being you while you're sitting there. You're only causing 50 cents worth of harm to you. I mean, I guess they say that nobody thinks their own fart stinks, so it's kind of like that to some extent. So how many of you will now get rid of your pollution? How many would choose to get rid of their pollution? So why would you get rid of your pollution?
My birthday's on the 1st, and it seems like it would make sense to bear a little bit of the cost for that kind of event.
Because you are providing benefit to other people, and you're a very kind, pro-social person who brings a lot of value added to the world and to your spouse possibly. And so that's a good thing of you to do. And some people will do that. I mean, the most of us, a lot of people are not going to. Somebody in the 31st may not get rid of their emissions, and maybe they shouldn't, but some people will get rid of their pollution. So altruism is a real thing. Pro-sociality is a real thing. Got colleagues that are excellent at studying these kinds of motivations and what they do in the world. However, I don't know if we want to rely on that to save the planet. We probably want something a little bit more than that. We want incentives in the market to actually make sure that we do more than that. So you don't actually have a purely, narrowly economic incentive, material incentive to reduce your emissions. So then we need to think about, well, okay, there's this externality. How can we kind of close that gap? If I knew your birthdays, if I had a roster of all your birthdays, then I would know who should be reducing their emissions and who shouldn't. And I guess if you were my students, I could sanction you a letter grade or something if you didn't do it, and I could pretty quickly bring you into compliance. So if I knew all of your information, I could pretty easily bring you into compliance. However, I don't know your birthdays for the most part, maybe almost none of you. And in that case, I'm going to be a little bit up a creek, and I'm in the situation the government's in when they try to regulate firms. The government doesn't know all of their costs, all of their options, all the things they can do. Firms usually do know their own situations and options and costs. And so we need the right firms to do the right thing without knowing who they are and even who should be doing what. And so then how can we do that? All right, so now I'm going to say, you people in the left half of the room, to my left, you're going to reduce your pollution, and everybody to my right, you're scot-free, you keep going. So what is your birthday? What day of the month? 29th. Okay, so I'm already doing pretty badly. So the first person I chose had a birthday on the 29th. They created $15.50 of value, lost $29 of value. That's not too good. So let's get somebody on the right half of the room. So when's your birthday? 15th. So again, I'm doing pretty bad. This is somebody who should have reduced their emissions who didn't. I think that's about as bad as I could have done. Well, if you were in the first, I would have been doing even worse. And maybe you could have been the 31st and helped me out a little bit. But anyway, I'm doing pretty bad. This is a pretty crude rule. So maybe there are better things I can do. There are probably a lot of better things I can do than that, apparently. So this is probably a poor way to do things because we'll actually get to about the right level of pollution. We know that probably half of us should get rid of pollution and about half of us are on the left-hand side of the room. But the wrong people are going to do it and we're wasting resources unnecessarily. So we're going to end up wasting resources and maybe there are other things we can do. So instead of that, what if I say you pay me $15.50 if you keep polluting and you have the option to stop polluting? So how many of you are going to stop polluting now? So when's your birthday? What day of the month? The 15th, and you chose to stop polluting. Why? How much are you going to save?
I don't know. I'm going to save 50 cents.
Yeah, math, right? Girls can do math too. So 50 cents. So we're creating 50 cents worth of value, and that's the right decision. And if your birthday had been on the 31st, you would keep polluting, and it's actually the right thing to do. You're not creating value if you stop polluting in that situation. So we're actually getting to about the right outcome. without me having to know anything other than what's the social cost of pollution and then making you pay that to me. And I don't need to know your private information or private situation. And this is called a market-based solution. We're using a market to get us to the right outcome, where in general, like with any other market, I don't need to know all of your details. All I need to tell you is the missing cost and then have you make your own decisions from that. So by putting a price on pollution, we make the market work. We can do that either by putting a price on pollution directly, like we did in that example, or by capping the total quantity of pollution and then letting firms figure out things among themselves, or individual people, however you want to do it. So imagine we have a refinery that has various ways it can get rid of pollution. We have a power plant that, let's say, just doesn't have many things it can do. It's already been built. It's a power plant. What's it going to do? So we give a couple units, a couple permits, or 4 permits to this refinery. We give 4 permits to this power plant. The refinery is like, I don't actually need all these. I could sell some and just do other stuff. The power plant's like, I should actually use some more permits. It's pretty expensive for me to do anything else. I need a permit to pollute. So they might pay the refinery. This is the end trade part. They can pay the refinery for some permits, and the refinery is now going to cut their emissions a bit more than the power plant, and the power plant will then keep emitting, and we've reallocated emissions between the two of them. This is the same outcome as what you would get with a carbon tax. It turns out you can actually, if you set the policy right, the price of the permits will be the same as the tax you would have imposed. It also turns out it doesn't matter how you allocate these permits. You could have given them all to the power plant. This is the Coase theorem for those of you who've seen it. Could have given them all to the power plant, could have given them all to the refinery. You could have auctioned them and kept the money for the taxpayers. You get to the same real outcome either way. You just need to define a property right and then let people trade among themselves. So this is cap and trade, and to first order, economists don't really care which one you do. There's a mapping from prices to quantities. You can regulate a price and let the market find the quantity. That's an emission tax. You can regulate the total quantity and let the market find the price, and that's a cap and trade system. There are some subtle differences we can talk about later if you're really intrigued by it, but for the most part, they're pretty equivalent. So market-based policies have been pushed by economists for more like 40 or 50 years now, and they were originally just kind of a theoretical curiosity because they were not the way regulation was done. The Clean Air Act, Clean Water Act, all of that, those were not market-based policies. Those are what we call command and control. We started seeing market-based policies emerge in the 80s through US federal regulation, and in particular, the signature regulation was George H.W. Bush's acid rain program in the 1990 Clean Air Act amendments, and that was originally a Republican policy. The Republicans really pushed market-based instruments at that time. And it turned out, this is how we regulated sulfur emissions from coal plants. The beauty of this story was that we had predictions for what the costs of the policy were going to be. And the backup had been to just regulate it in a traditional way by telling coal plants to install this technology that would clean their exhaust. And we thought that's what they would do if we built a market for them anyway. Once they had a market, they had an incentive to find what the cheapest thing to do was, and they realized that, well, you don't have to burn coal with a lot of impurities that makes acid rain. You can burn lower sulfur coal that doesn't make as much acid when it goes up into the air. But to do that, you have to get that low sulfur coal from Wyoming to the Midwest and the East where the coal plants were. That seemed hard, except there had been railroad deregulation not too long before that made it a lot cheaper to transport it. So instead of installing this big, expensive piece of equipment to clean their emissions, they lowered their emissions by just changing their coal source. And it's something that the analysts in the government hadn't predicted, and it made the policy come in much cheaper than had been expected. And that's why we use market-based instruments, because they can achieve that kind of outcome. And the real pollution outcome was unchanged. I mean, either way that we met the cap. We're using this already to regulate greenhouse gases like carbon dioxide, and I'll come back to that in a few slides. So what would a carbon price do? So as Joellen already went over, we have a few things that we get carbon from. We have coal, we have natural gas, we have gasoline, and then we have these non-carbon things, solar panels, wind turbines, and nuclear power plants. So what would a carbon price do? So you burn coal, you're breaking the carbon-hydrogen bonds, you're making energy, great. Hydrogen combines with oxygen, makes water. Carbon combines with oxygen, makes CO2. There's a lot of carbon in coal. It's lumpy. It's a giant lump of carbon, basically, almost like a diamond. So you're making a lot of CO2 per unit of energy. So the price of the coal is going to go way up if you have a carbon tax, and the quantity that we use is going to go way down because it got more expensive. Natural gas has 1 unit of carbon per 4 units of hydrogen. It gets a little more expensive. There's not a lot of carbon per unit of energy. We might actually use a bit more in the near term because it's going to replace coal. It'll get relatively cheaper compared to coal, even as it gets relatively expensive compared to something like solar, wind, or nuclear. In the long term, we end up using less of it. Gasoline's in between the two. It'll get a bit more expensive. It's hard to reduce emissions too quickly. We probably would still use a decent bit, but use would go down, and more so over time as we change vehicles and all that. And then one of the big changes is things like solar, wind, and nuclear will grow dramatically. Their price didn't change, but they look attractive relative to the other stuff they're competing with. And in the long run, things that can actually suck CO2 out of the air, right now there's no economic incentive for these. These technologies are real, they do exist, and with an economic incentive, they would start getting cheaper. And that incentive would then be in place, and I'd predict we're going to be doing that by mid-century, if not much later. So we're basically not imposing a carbon price, we're removing a carbon subsidy. There is a correct price for carbon. Right now we're below that price, so we're implicitly subsidizing carbon emissions by bearing the cost of those emissions out into the future. So fuels with a lot of carbon get more expensive. That leads us to want to substitute natural gas for coal. We're already doing a lot of that anyway. That's why our emissions fell so much in the last 10 years. Also, renewables and nuclear would have an edge. Electric vehicles would look more attractive in places that have a low carbon electricity source, and they wouldn't look relatively attractive in places that have a high carbon source. And that's actually good. You want some places to use them and some places maybe not to. Raising the price of carbon-intensive energy would also have a spur for more efficient appliances and more efficient vehicles. That's another important margin we should be pushing on simultaneously, along with switching supply. And then finally, firms would start doing more R&D. So if there's actually a market for low-carbon technologies, if there are more of one, then firms are going to invest more in developing them. And we've seen in solar and wind and electric vehicles how quickly things can change when you do that. What else could we do if we didn't want to do a carbon price? You could pay people to produce green electricity. They do that in parts of Europe. Or in much of the US, including Arizona, we require a fraction of electricity to be renewable. That does some of what a carbon price would do, but it doesn't incentivize nuclear or shale gas instead of other stuff, so it's missing some big margins. It also doesn't necessarily raise the price of electricity. It could, depending on the policy, but it doesn't have to. And one margin you'd want is to actually reduce energy use as well and increase efficiency, and you're not really pushing that margin. What if you require a different transportation fuel, or require more efficient cars, or require a different kind of fuel source for transportation? Well, that's pushing on a margin, but what if you pick the wrong technology? 15 years ago, we would have said require fuel cells. Now we probably wouldn't. We'd probably say EVs, and maybe in another 10 years, that might look like the wrong choice. And then also, you still want incentive to drive less, and you're not necessarily giving that incentive. And in fact, you could be given an incentive to actually drive more if you require more fuel-efficient cars. So you're not pushing on all margins at once. And then finally, what if you just fund new technologies? The government does a lot of R&D. This is probably a really critical part of policy, but it's also a critical part of policy to have a market for those technologies, in part by having a price there that makes them viable and want to be used. So most economists think you should do this along with the carbon price because there are other market failures that are in play there. So then thinking what's actually going on in the world and what do we need to be doing over the next decade? So kind of moving toward wrapping up. So global agreements, Paris, Copenhagen, a few others, have targeted 2 degrees and possibly, ideally, 1.5 degrees of warming and no more than that. What does it mean to meet that? So here are some scenarios for how we could achieve that. We're looking out from the present day out to 2100, and we're plotting emissions over time. And the next decade, we're kind of locked in. If we're going to meet these targets, we need a pretty steep decline. That's basically this generation's challenge, is to hit that decline out to 2050. And this is why you're seeing these mid-century net zero targets popping up by cities and utilities and countries, because they're looking at these graphs knowing where they need to be by the middle of the century. So this is a big challenge. How can we get there? What are we doing? Well, the US almost passed a cap and trade program in 2009, 2010. It passed the House of Representatives, in fact. This was what emissions would have been without it. This is what the cap would have been, so what they would have been with it. Pretty ambitious reduction in emissions. It would have been a pretty real policy. Came within one vote of going forward in the Senate, but couldn't block the filibuster due to some stuff that happened at the last second. So we don't have this policy. We have no coordinated federal policy for a price on carbon. Other countries and entities are doing stuff. It doesn't mean stuff is not happening. So much of Canada is being subject to climate regulation now and in the near future. The northeastern United States has a cap and trade program. California has a cap and trade program. Mexico's been looking at cap and trade as well. European Union's entirely under a cap and trade program. Many parts of China have pilot programs for cap and trade as well. So there's a lot more happening than one may think. None of these programs are super ambitious or super stringent, but they're actually programs, and they're figuring out the kinks and working them out. And there have definitely been a lot of kinks that have been worked out over time. But on net, the total carbon pricing we're doing around society is actually not that much. Globally, this is a pretty small amount of money that we're actually making firms pay through carbon pricing. In the meantime, we are actually directly paying for renewables and electric cars. But even adding these two together doesn't get us anywhere near to the amount we're actually paying in order to have fossil fuels burned. So we actually not only don't have a positive carbon price, we actually implicitly have a negative carbon price. We're actively amplifying the externality because of all the subsidies that exist globally to burn fossil fuels. There are parts of the world you can literally get paid to burn fossil fuels, and on net, that is the situation worldwide. And that's not a positive thing in terms of the market failure. In the current US Congress, there are several tax bills. So there's more momentum for a carbon tax right now than for cap and trade. This is a summary of what they look like, and there are some that are bipartisan. They tend to start low and then ramp up over time. The emissions profile isn't radically different, maybe a little less ambitious, but not radically different from what the cap and trade would have done 10 years ago. So this is what emissions would be without the policy, fairly flat, because we now have shale gas instead of coal, and they'd be falling over time with the carbon taxes going up over time. Those carbon taxes are going to raise revenue, anywhere from $100 billion to $500 billion per year. What should the government do with that? So you could imagine, and what a lot of economists would like, is cut other taxes. We have other taxes because we need to raise revenue to fund stuff that we like and that we need. Those taxes often are distortionary or disincentivizing work or something like that. Trade those out for a tax that corrects an externality. That would be a win-win. That would be a positive thing. You could rebate the money to everybody equally. This is cap and dividend or carbon dividends, different names for that. So like in Alaska, you get an oil check. You could basically get a carbon check every month or year from the US government. We know we need to do R&D and infrastructure for adaptation, so we could fund that out of the money. You could compensate firms who are exposed to areas that are trading with you that don't have carbon regulation. That could be one use for the money. You could help people retrain and adjust in areas that especially get hit by a transition away from a high carbon society. That's a use that would almost certainly be in any bill. One thing you probably shouldn't do, which is what a lot of our old policy would have done and what a lot of policies around the world have done, is just give the permits away for free. Politically, you may need to do that to get it passed, and if that's true, that is what it is. But economically, you might as well raise money for the taxpayers and then do something productive with the money, which may include just cutting other taxes. So if you give permits away, you're literally giving valuable property to firms that was coming from the taxpayers to them. And that's something that can be hidden in the policy. So the upshot, so there are some arguments floating around, and some that have been made by fairly prominent politicians recently, that climate policy might be essentially free. That would be nice, but probably any reasonably ambitious policy is probably not going to be free. Doing things that are hard can have cost. That doesn't mean it's not worth it, though, because there are also benefits, and the benefits may offset the cost. But because those costs could be substantial for a reasonably ambitious policy, it's important not to make those costs more than they have to be by putting an inefficient policy in place. And this is why a lot of economists think it's so critical to actually get to correcting the market failure directly through a carbon price. Because if the cost is going to be substantial and there's only so much political will to get it done, then you can't go amplifying that cost by another factor of 2 or 3 if we want to make progress. So thank you, and I think we're happy to take questions for the next while.
Thank you for the excellent talk. I had a question about if you guys are worried about countries gaming the system in the future, in a hypothetical situation in which these carbon, nationwide bills came due. Are you worried that some third party might try to influence your robo-carbon float ships? That's my question. Thank you.
They can try. No, quite seriously, it's very difficult to do. The reason we use robot floats, everybody says, why not ROVs, why not submarines, why not whatever? And the reason is the law of the sea. The law of the sea says if you drive something into somebody's exclusive economic zone, in the coastal areas, et cetera, you have to have a permit. But if it drifts in, it's legal. So my robot floats go everywhere. They are legal in the ocean. They can send me back the data legally. They're incredibly hard to find. They're about yay high. They're about so thick, and they have absolutely no emissions. They're battery driven. They're passive sensors. I triple dog dare you to find one. No, quite seriously. We have a hard time recovering them, and we know right where they are.
I think the answer is no. Great, thank you. So I think it is a highly nonlinear problem, and the models we're looking at are nonlinear. I myself have worked on bringing tipping points into these models. I think that's really important. The problem is we don't even know exactly how to model that scientifically, but we do the best we can. A lot of it, I was very clear, a lot of this, there's a lot that we just know we don't know and that we won't even know until after we get there. And we're going to do the best we can to hit that. We're working on that. People are thinking about that.
So we're going to do nothing?
No, in terms of the politics, how do you make the price happen? That's a question beyond our disciplines. Happy to talk about that offline, but we can talk about what the price should be and how to model these features, and we can have a technical conversation about that. But the political will, how to make it happen, I think it's going to be a different question. It's just beyond what either of us can engage with, probably. It's a hard problem. People around the world are moving. There is stuff being done. Whether it's happening fast enough or not, stuff can change pretty quickly. We've seen that in a whole range of issues in the last 10 years. Already, the price of solar panels is not what it was 10 years ago. Electric cars are now where you would have dreamed 5 years ago they'd be where they are today. So we're on the precipice of stuff being able to change fairly quickly. You can have a social tipping point like you can a natural science one. Whether it'll happen, I don't know, and nobody can see the future. But it's not clear that it could be really bad or it could be a lot better than we fear, and we're not going to know until we go through it.
I actually agree. I think we can move a lot faster than we think we can. I'm quite certain. And most of that is just because over the last 10 years, we've really started to move, and we haven't even gotten organized. So my hope is that yes, it's going to take, because we have been leading in technology worldwide for so long, it's going to take American leadership. And it's going to take American votes and American taxpayers stepping up. And the way I think about it is, frankly, it took us a long time to get into World War II. Everybody said it's Europe's problem, we shouldn't get in, it's not that big a deal, Hitler's not so bad. How many people did they say were dead? Wait a minute. It was very...
And we mobilized in 6 months.
And we did. I exactly think that we are not less determined than our grandparents. We are not less ingenuity. We're not less innovative. We're not less hardworking. We can absolutely do this. And it's our turn, and we're going to do it. It is going to take everybody getting out and voting. We are going to have to make it a priority. And it's going to have to start in states that have already seen the biggest impacts, because people already feel it. You can't just say there's some externalities. I'm sorry, cabin fever and my bigger electric bills are a direct impact, and I have to pay them every year. It makes me cranky. I think that's not just me. I think it's all of Arizona. And I think we can make a big impact. I think we have not gotten organized yet. You're absolutely right. And I have a friend, Jim Hansen. I've only met him a few times, but I think of him as a friend because he's a classic carbon scientist, and he chains himself to coal trains and gets arrested on a regular basis, and he does it for his grandkids, right? He says, Opa will not be thought of by his grandkids as the guy who did nothing. Now, I'm not going to chain myself to coal plants because I have little kids and can't be away from home in a jail cell. I think I have better things to do, but at the same time, I live and work in Arizona. I came from New Jersey, right? From a big, basically blue state to a big red state to do my work and make my home. And I love it here. And I think we could be one of the states that actually helps literally turn the tide. Because if we can do it and make California jealous, then why couldn't everybody do it? I mean, quite frankly, I think we all like competition, and we just haven't made up our minds that we have to get into this fight. But we made 100,000 planes in a month. We can do it. We can do it. My great aunt was the first woman engineer at Boeing. I know we can do this. We just haven't made up our minds. So I'm just trying to show you the science, and I do it over and over because I believe that if you can show that we know who's doing what to whom, that we should get into this, that the impacts are going to keep growing and are going to get worse, that we do have to worry about losing our biggest naval base, and not just that one. We need to save lives and property, and our innovation we can sell to the world because they would like to innovate like we do. We have 52 of the top 100 universities in the United States in the world, 52 of the top 100. Who, if not us, who?
Yeah.